In 1931, it was the biggest bridge in the Big Apple. Today, it's grown to become the busiest in the world. It's the unfinished masterpiece across the Hudson River and one of the main arteries that keeps the heart of New York City pumping. Now, the George Washington Bridge on Modern Marvels. Spanning the storied Hudson River between Fort Lee, New Jersey, and Manhattan's Washington Heights stands the George Washington Bridge. Its gleaming towers and intricate interwoven steel distinguish this as one of the greatest bridges in a city known for great bridges. When opened on October 25, 1931, it was the longest in the world. At 3,500 feet in length, the main suspension span was more than double the distance of the previous record holder, the Ambassador Bridge in Detroit, Michigan. Today, the two-level George Washington, referred to by locals as the GW, impacts the lives of thousands of motorists and consumers who call New York home.
We have about 330,000 vehicles a day and over 550,000 people per day. And it really is nothing more than an intersection between two states. And it's important to the commerce of the two states, not only people getting to work, but about 30,000 trucks a day that have to get the freight and goods from the ports to New England and to elsewhere in the entire Northeast. So the George Washington Bridge is an incredibly important link to the economy of the entire New York metropolitan region.
To keep up with the tremendous traffic burden, the Port Authority of New York and New Jersey, charged with running the bridge, has to constantly maintain the 14-lane hanging highway. In 2002, the Port Authority began one of the largest projects in the bridge's history. At a cost of nearly $70 million, the bridge is getting a new paint job. Today, motorists making the world-famous crossing see less of the renowned structural steel and metalwork than scaffolding covered with tarps.
Well, here we are at the New Jersey Towers section of the George Washington Bridge. We have been removing all the red lead that was painted on when the bridge was first made. This encompasses erecting this huge, humongous scaffolding and enclosing it. That's to prevent the red lead from becoming airborne and becoming an environmental problem. This has been going on for a couple of years. Once this is completed, we will move over to the New York side and do the New York Tower as well. It's time-consuming. There's a lot of steel here, approximately 113 million tons.
The Port Authority is going to extremes to keep lead paint from contaminating the river. That separates bustling New York City from the rest of the country. The first attempt to build a bridge across the Hudson was seriously proposed just after the Civil War in 1868. Officials excited by the planned Brooklyn Bridge that would connect the eastern side of Manhattan with Brooklyn saw the Hudson Bridge as the next logical step. But unlike the Brooklyn crossing, the Hudson Bridge would be required to carry heavy rail lines to help bring supplies from other states into the city.
A 3,200-foot span to carry railroad cars, which are very heavy at the time. It hadn't been done before. Even the Brooklyn Bridge, which was being conceived, was really not a major railroad bridge. That wasn't its primary function. It was going to carry a light trolley and actually pedestrians. But a heavy bridge for railroad cars became much more of an issue, especially the long span. So it didn't go forward.
But the dream wouldn't die. In fact, in typical New York fashion, it only became larger.
The next major step was in 1890 when the North River Bridge Company was formed. And the head of the engineer for that company was a fellow named Gustav Lindenthal, who was a famous engineer at the time and had been building railroad bridges and long-span bridges.
Lindenthal was the kind of engineer that we're familiar with from the 19th century. He thought big, really big. Even for New York that likes big, he thought big.
Lindenthal envisioned his enormous bridge connecting West 23rd Street and Hoboken, New Jersey, with 12 railroad tracks.
The companies that most wanted a bridge across the Hudson were the railroad companies, and they were extremely politically powerful at that time. So part of the reason that Lindenthal thought he could build a monster bridge across such a wide part of the Hudson was that he had some of the biggest players in American capitalism backing him.
But critics pointed out that a massive midtown bridge would eat up too much valuable Manhattan real estate.
If you can imagine that you have the lower sides over here on both sides of the river, this being New Jersey, let's say, and this being Manhattan, and then having to build a bridge above the river level some 150 to 200 feet so boats can pass underneath it. That means that you have to build a rather large approach. And those approaches to get the bridge traffic up to that level require quite a bit of real estate and taking of land. And that's always been a major issue in terms of long span bridges and their approaches in very highly densely populated areas.
Even with his powerful connections, Lindenthal couldn't find the financial backing for his vision. Once again, the bridge became a dream, and remained so until 1923, when the Port of New York Authority was charged with the responsibility to build a bridge across the Hudson. Again, Gustav Lindenthal returned, but this time his plans were even more grandiose. His new proposed bridge was so large, its two 840-foot towers would be taller than the tallest building in the city. The 16-lane, 18-track span would stretch over a half-mile and even have a skyscraper as part of the structure. But times had changed. The once mighty railroads were losing their hold on transportation, and automobile travel was coming of age. With a price tag of $180 million, the bridge was politically impossible to sell. One of Lindenthal's strongest critics turned out to be his own protege, the Swiss-born engineer, Othmar Ammann.
He had worked with Lindenthal a few years before as his first assistant under the construction of the Hellgate Bridge. So Lindenthal knew him well, realized him as a reliable person, and for 2 years they worked on plans for the bridge, and Father slowly realized that Lindenthal's plan was not practical.
Both quiet and at 5 foot 4 inches tall, unimposing, Ammann nevertheless impressed the governor of New Jersey, George Siltzer, with his ability and practicality.
Governor Siltzer played an important role in this whole story of the George Washington Bridge in that he was a good friend of Lindenthal, but behind the scenes was encouraging Father to go off on his own for a bridge that would be more practical.
In March of 1923, Ammann split from Lindenthal. In a letter to his parents in Switzerland, he complained about the turmoil his former boss had caused and explained his own plans for the future.
In vain, I, as well as others, have been fighting against the unlimited ambition of a genius that is obsessed with illusions of grandeur. He has the power in his hands and refuses to bring moderation into his gigantic plans. Instead, his illusions lead him to enlarge his plans more and more until he has reached the unheard-of sum of $500 million, an impossibility even in America. However, I have gained a rich experience and have decided to build anew on the ruins with fresh hope and courage. And at that, on my own initiative and with my own plans, on a more moderate scale.
Ammann had been working on a design for a bridge with 6 lanes for vehicles and an additional lower deck for light transit, to be added at a later date. The location for his bridge was further north, around 179th Street, where acquiring land would be less of an issue.
Ammann's site offered some other advantages too. The landmass on both sides of the Hudson River were highly elevated, so that the road deck itself would be many stories above the water level of the Hudson River, and there wouldn't be a navigation problem with tall ships passing under the bridge.
The second factor would be the location that Othmar picked, which was one of the narrowest points at the river, and be able to build a long span bridge. It was going to more than double anything that had ever been built.
In 1925, with the governor's clout backing him, Ammann was hired by the Port Authority as their master bridge designer and chief engineer.
It is hard to describe why Father was able to inspire confidence in people. He had a manner about him. He was a very quiet person, and yet when the time came to say something, it was listened to.
The ironic twist in the story of New York's bridges is that the person who wanted to build them didn't basically get to build them, and the person who was the meek little assistant who came in as an apprentice into the big engineer Lindenthal's office is the one who ended up building most of New York's famous bridges.
The groundbreaking ceremony on September 21st, 1927 was the start of a 4-year construction process and the beginning of the career of one of the greatest bridge builders the world has ever known. His first challenge? Finding a rock-solid foundation at the bottom of the Hudson River to support the biggest bridge in the world. Work crews began the epic job of laying the new Hudson River Bridge's foundation on October 21st, 1927. The two most noticeable and structurally significant pieces of the bridge, the towers, needed to be built on firm footings to support the enormous weight of the structure. On the New York side, a narrow outcropping of land offered an excellent location. But on the New Jersey side, the only solid ground was at the bottom of the Hudson River.
They couldn't sit it on land. It would have made the span just beyond what Othmar Ammann had determined would be both feasible and physically able to do. So they had to build the foundation in about 60 to 70 feet of water, which had not been done before.
In the past, engineers had built smaller underwater foundations with the use of caissons. Caissons are metal and wood boxes with an open end. For bridge building, they are dropped to the bottom of the river, like an upside-down coffee cup, and pressurized with air to remove the water. Workers then enter into the caisson through an airlock to excavate or lay cement. But those who spent long hours in the pressurized compartment were at risk of suffering the bends. Upon leaving the caisson, nitrogen, which over time dissolved in the workers' bodies due to the pressure, quickly turned back into gas. The bubbles forming in the bloodstream were extremely painful and could lead to paralysis or even death. To avoid the dangers of caisson construction, Ammann and his team of bridge engineers decided on a different technology to build the New Jersey Tower Foundation: a cofferdam. A cofferdam is a watertight shell stretching from the river bottom to the surface. Once built, workers pump out the water, forming an open shaft to the river bottom.
They were then able to build and construct the foundation for the tower within the dry. And this was a huge economical savings.
Even though bridge engineers deemed the cofferdam to be safer than caissons, building on the bottom of a river is always a dangerous endeavor.
During the construction of the cofferdam on the Jersey side, 3 men were working at the base 70 feet down, and unfortunately one of the walls failed and water flooded in. It flooded the entire cofferdam, and these 3 men unfortunately did drown.
Despite the tragedy, bridge designers still believed the cofferdam was the best and safest way to build a foundation.
After that tragic accident in the cofferdam, once they repaired that and they were able to totally unwater the cofferdam again and seal it properly, the seal was so effective they were able to use a small little pump that you could buy in a hardware store, and it was enough to keep the water out during the entire time of the construction.
With the water removed, workers resumed their jobs inside the cofferdam, digging through an additional 20 feet of river silt to reach bedrock.
No one had ever gone to that depth before. And so this was the first time where you saw a cofferdam construction in a major river to that depth. And after that, it became commonplace, but it was really a first, and it was done at the George Washington Bridge.
Finally, workers pumped 37,500 cubic yards of concrete into the dam, creating an 89 by 98 foot solid foundation for the next phase of building, the tower construction. The design of the two 604-foot towers changed drastically between the planning and construction phases. Othmar Ammann originally envisioned mammoth masonry and steel structures, similar to those on the Brooklyn Bridge.
He, as a young man in New York, really fell in love with the Brooklyn Bridge and always held that as a model for the ideal suspension bridge. He felt the stone towers for the George Washington Bridge would be particularly appropriate because the rock faces of the Palisades on the New Jersey side and the exposed granite on the Manhattan side would blend with stone towers as though the towers themselves were part of the natural landscape that just sort of grew out of the riverbed.
But it soon became apparent to Aman that the bridge was being overbuilt, which was a waste of money and materials.
So Aman didn't give up the idea of masonry, but then shifted gears, hired an architect, Cass Gilbert, and they began working on schemes to design a stone wall to hang on to the steel framework that would be there strictly for ornamental purposes.
To hold the stone facade, Aman redesigned the interior steel framework into a tight and intricate latticework. Unknown to Aman at the time, the design would eventually be considered the bridge's crowning architectural achievement. Started in May of 1930, much of the two soaring towers construction was actually done at ground level. The prefabricated steelwork was moved into location via barges on the New Jersey side and trucks on the New York side. Workers used an erection traveler, or movable crane, which was set up between the tower legs and climbed or descended the structure as necessary. Atop the erection traveler, workers used electric winches to lift the over 20,000 tons of steel that made up each tower. They then riveted the steel into place. But in the end, no amount of physical labor or design prowess could finish the towers as Aman had envisioned them. The bridge that had begun construction in the Roaring '20s would be forever undressed by the Great Depression.
The circumstances had changed tremendously. We went from building a bridge in the prosperous 20s to finishing a public project at a time when the economy had crashed, people were living in shacks in Central Park, and people were worried about whether they could put enough food on the table, let alone have grand public works.
As a result, the towers were left bare, and what was originally seen as a cost-cutting measure has become one of the most endearing and celebrated features of the bridge: its exposed steel frame.
So in the end, by not putting the stone in place, they have revealed a tightly knit underlying structure that still conveys the outline of a massive form, but in fact, when you get inside it, it's just three-dimensional lacework, very pleasing to the eye, and modern looking, the way the Eiffel Tower is modern looking.
But while one group of engineers was trying to finish its job without stone, another group was busy making one of the largest concrete blocks the world had ever seen. On the Manhattan side of the bridge, workers began the epic task of creating an anchorage worthy of supporting the largest bridge in the world. From a distance, the graceful bend of a suspension bridge's cables seemed to effortlessly dangle the road above the water. But in reality, the cables are under constant strain to support the bridge's weight and every vehicle that crosses. To resist the tension, all suspension bridges must have sturdy anchor points. And as the length and weight of a bridge grows, so must the strength and size of its anchorages.
The design of the anchorages for a suspension bridge are fairly simple. Essentially, they are designed to resist the pull or the tension in the main cables that comes from the weight of the bridge and from any live load or wind loads that are applied to the bridge. Traditionally, these anchorages are usually embedded deep into the rock.
In the spring of 1930, builders on the emerging Hudson River Bridge were creating what nature had not: a good anchor point. On the New York side of the river, Othmar Aman, the bridge's designer, had decided a massive concrete and steel block needed to be constructed to hold fast the eastern side of the bridge.
There were several sites potentially for the anchorage. One was in Fort Washington Park proper itself, and the other would be up on the Riverside Cliffs. The Fort Washington Park location would require a very large, massive concrete and masonry structure to be situated within the park. A lot of the people in the New York area, and specifically up in that area, envisioned this as not being very aesthetic, and actually tried to get Amman to move the anchorage eastward back up onto the riverside cliffs. This would have resulted in a much longer span to the structure, would have increased the cost of the bridge because the longer span equates to more steel towers, more foundation costs, more cable costs, etc.
Fearing budget overruns, Amman fought hard for the Washington Park location and won. Still, the park was far from perfect for the anchorage construction.
Bedrock is significantly below the ground level in that park itself, so that would have required some extensive work in that park. And what Amman and the designers came up with at the time was to just basically build a huge weight or block within the anchorage itself to resist the pull and the forces of the main cables, and therefore reduce some of the excavation costs that would normally be required for typical suspension anchorages.
With the groundwork laid, bridge workers poured 110,000 cubic yards of concrete to form a 200-foot wide, 290-foot long, and 130-foot high massive anchorage. When completed, the mammoth block weighed in at over 260,000 tons. At the time, the largest bridge anchorage ever made. Normally, suspension bridges have two concrete anchorages. But Othmar Amman recognized a convenient natural substitute on the New Jersey shoreline. Amman theorized that the New Jersey Palisades into which the bridge was being built were sturdy enough to hold the bridge's cables in place.
When they had to build the anchorage for the New Jersey side, they actually had to dig down into the Jersey trap rock or cliffs, and excavating this was a monumental task for the time in 1931.
Engineers bored a 150-foot deep tunnel into the cliff face and excavated nearly 200,000 cubic yards of solid rock.
They dug down and they carried all the excavated rock into these muck cars and carried them away, and then they used the crushed rock in the aggregate for the concrete.
Next, workers placed steel braces and filled the tunnels with concrete. The final product was a foundation as strong as the cliffs themselves, easily able to hold its share of the weight. With the anchorages in place, another group of workers began their job of constructing the four massive main cables. When strung between the two anchorages and over the towers, the cables would physically hold the weight of the road below. Othmar Amman and his design team debated what type of cable would best suit the GW. Early in the planning stages, steel eye-bars, which had successfully been used in the construction of the Queensboro Bridge, seemed a likely choice.
At the time, there was a discussion about whether a wire suspension bridge cable was more economical than a chain link or eye-bar cable. Eye-bars being heavy metal bars that look almost like a chain, a modern-day chain. And there was some discussion on long-span bridges on which one was more economical to construct.
Since bridge cables don't distribute the weight of the bridge evenly, some sections of the cable experience tremendous loads, while others relatively small loads. Wire cable is faster to install, but must be uniform in thickness, which wastes material. Eye-bars can vary in thickness according to the loads they will carry. That means less material is used, but they take longer to forge and install.
Based on the discussions back and forth regarding the type of main cables to be incorporated for the George Washington Bridge, Amman and his engineers actually put out alternative designs, and they left it up to the contractors to bid the job to see which was the most economical solution. Contractors bid the job. John A. Roebling and Sons won the job with the low bid, and their bid was for wire cables, and this is why we have wire cables on the bridge.
The engineers at the John A. Roebling and Sons Company were extremely well versed in the techniques of suspension bridge cable construction. The firm's previous experience included building the Brooklyn Bridge.
And they invented aerial spinning and technology and the methods for aerial spinning as we know it actually today.
For safety and to give bridge builders a place to work high above the water, The first step in aerial spinning involved building a catwalk. To begin the catwalk, workers on barges pulled guide wires between the two anchorages. A team of 9 men on a rope gang then used block and tackle to lift the wires to the top of the towers. Once in place, a trolley was installed on the wires to carry the men hundreds of feet above the water. Finally, the individual pieces of catwalk were hoisted up the wires or lifted into place from barges far below. With the catwalk finished, the cable spinning could begin. Electric winches powered 2 spinning wheels that pulled the pencil-thick individual wires from anchorage to anchorage.
Each main cable contains wires like this. Each main cable contains 26,474 of these wires. Each main cable can withstand a pull of 180 million pounds.
Enormous reels, each containing 30 miles of steel wire, were brought in on rail cars.
It was an amazing feat. The logistics had never been done to that great a height and that great a distance across a river before.
It took 300 workers, 209 days to spin the over 100,000 individual wires of the 4 main cables. But fully half the work was done, with an eye towards the future.
They envisioned an explosion of traffic in the coming years, and they knew that eventually, in order to meet the demand, that they would need a second deck.
The proposed lower deck had always been part of the plan. The difficulty for Aman was deciding when to build its cables.
At the time, Aman even considered only designing and constructing 1 cable to support the 1 roadway deck. But based on the geometry of the New Jersey anchorages and the construction methods to build the New Jersey anchorages, they opted to actually put the second cable up during the original construction. And that actually proved probably to be a very economical solution.
The final step in cable construction was making 4 cables out of the thousands of individual strands of wire.
The main cables are built in a hexagon configuration. After the hexagon configuration is totally complete, they are compacted using 12 jacks in a radial configuration, and these wires are then squeezed to a round configuration. They install the cable bands, those huge steel casings that you see on the cables.
When finished, the 4 36-inch diameter cables weighed in at 28,100 tons and were ready for the next and final step, receiving the roadway. From 1927 to 1930, bridge builders had labored constructing the suspended link between the west side of Manhattan and the rest of the country. The final step in completing the George Washington Bridge was hanging the roadway onto the massive cables. For cost savings and ease of construction, Othmar Aman, the bridge's designer, took a chance on a design theory that had never been tested on such a large scale.
Just prior to the design of the George Washington Bridge, engineers had been developing new methods of analysis for long-span bridge structures. This is the deflection theory. And the George Washington Bridge was the first very long-span bridge to really incorporate and take the deflection theory full force on in the design.
The larger a suspension bridge is, the heavier it will be. According to the deflection theory, once a bridge reaches a certain length, its own weight will keep it from swaying in the wind or shifting due to traffic loads. Most bridges utilize a design feature called a stiffening truss to keep the structure rigid. Steel frames in a box or triangular shape are constructed underneath the roadway to beef up the structure.
Aman theorized that the bridge, in terms of its width of its roadway, which was 106 feet across, which was the widest bridge at the time, the weight of the cables, you had 4 large cables weighing some 60 million pounds. The combination of that and the idea of deflection theory, that it did not require a stiffening truss to stabilize the bridge. It was rather a bold thought at the time.
The same theory, taken to extremes less than a decade later, would lead to one of the most famous bridge disasters of all time. With a span of nearly 5,000 feet, the weighty Tacoma Narrows Bridge should have been impervious to wind and traffic loads. But unforeseen by engineers, the long, extremely thin roadway took on the aerodynamic characteristics of an airplane wing. As a result, on November 7, 1940, a strong wind caused the bridge to become unstable. For well over an hour, the center span writhed and contorted before finally crashing to the river below.
The problem is balancing economy of material with stability of structure. And when engineers, particularly suspension engineers over history, began to push too hard on economy, later down the line, inevitably a bridge would fail, as happened again and again throughout the history of suspension bridge design.
But for Amman and the George Washington Bridge, the deflection theory gamble and subsequent lack of stiffening trusses paid off.
Why did Amman get away with building a bridge that never fell down? I think part of that is that he had a structural intuition, something that was really visceral. It's as though his body were the bridge, and he would imagine how the forces of compression and twisting and tension would be experienced by that structure. I mean, other engineers who followed the same scientific methods that he did and technology designed bridges that failed.
By the spring of 1931, the towers, anchorages, and cables of the George Washington Bridge were ready to accept the crossing's final component, the roadway. The bridge workers' first step was attaching the suspenders from the main cables.
This is a piece of suspender rope used in the construction of the George Washington Bridge. This is an actual piece of rope in building the bridge. This is 2 7/8 inches diameter, contains 271 individual wires.
With the ropes dangling from the main cables, workers used cranes to lift pieces of the roadway's substructure into place.
They actually had to raise up 106 feet long, 56-ton floor beams from the river here and hook it onto each suspender. After several floor beams were hooked into place, they installed what's called the lower cord. That connects the ends of the floor beam.
Builders started the road construction at both ends and worked towards the center, eventually meeting in the middle. The last step involved laying tons of concrete to form the roadway. The original 6-lane George Washington Bridge finally opened to traffic on October 25, 1931. 30,000 people witnessed the event, and countless more tuned in on their radios as Governor Franklin D. Roosevelt cut the ribbon and opened the bridge. But the true hero of the day, and the man most responsible for building the bridge, would remain largely unknown.
Well, I don't think there's any engineer who built more bridges for a single city than Othmar H. Amman did for New York City. Beginning with the George Washington Bridge, he went on to design and build the Bayonne Bridge, the Triborough Bridge, Bronx Whitestone Bridge, Throgs Neck Bridge, and Verrazano Narrows Bridge. He also designed the Lincoln Tunnels and oversaw the construction of the Midtown Tunnel. So even though New Yorkers are very aware of these bridges and tunnels, very few of them know that one man was the designer for all of them. Without Amman's bridges and tunnels, New York City would not be the city it is today.
In the end, the bridge would be seen as a construction anomaly, coming in both under budget at $59 million, a full $1 million less than planned, and ahead of schedule, 8 months early. The GW had other impressive qualities. As traffic demands grew, so had the bridge. In 1946, it underwent its first expansion. After World War II, years of stopped automobile production gave way to a car boom, and the bridge that had given such easy access to the suburbs was now feeling the strain.
The problem is that this commuting culture had the seeds of its own destruction within it, because the more it became easy to live outside the city and drive in, the more people wanted to do it. The more people wanted to do it, the less easy it became to drive in.
At completion, the center section of the bridge had remained an open steel grid. The paving of the center 2 lanes increased the bridge's capacity by 1/3, but the bridge wouldn't truly be finished for another 13 years. In 1959, the George Washington Bridge would begin its final metamorphosis, as massive increases in traffic warranted the building of another entire level of road surface. Fortunately, Othmar Ammen's foresight would again come into play. The 2 additional main cables spun during the original construction would hold the new deck.
The original design showed 2 lanes of light rail on the lower deck. But as time wore on, the automobile became more and more a prominent means of transportation, so then they decided that we're not going to use streetcars, we're going to design it for vehicular traffic.
Othmar Ammen was a visionary in many ways, and one of the many ways that we later New Yorkers can appreciate his vision is that even in the 1920s, he realized that there might be a need for more lanes on that bridge, and he built capacity into it so that it would be possible to build another deck in.
Workers hoisted 76 road segments from barges on the river below and connected them to the suspender cables. Next, they fastened the 2 decks together using thousands of bolts.
By phasing construction to be in pace with demand, they were able to build a less expensive bridge initially. And then as revenues came in from tolls for the bridge, they were able to set aside money to do construction at a future date.
Finished in 1963 at a cost of nearly $80 million, the construction marked the end of building on the GW. With a final renovation and additional traffic capacity, the bridge was poised to take the title as busiest in the world. Today, with nearly 500,000 people crossing every 24 hours, the bridge has donned that mantle. But what most customers don't realize is that the GW is more than just steel and concrete. It takes some cutting-edge technology to keep all that traffic moving. The George Washington Bridge is still the busiest in the world. With hundreds of thousands of cars and trucks crossing every day, the Port Authority relies on a small army of bridge personnel to keep the traffic moving and the bridge safe.
All told, there's about 350 people that perform various functions at the bridge, whether it's toll collection, emergency response, maintenance of the facility, and then the administration of all of those people, scheduling, timekeeping. And then on top of that, there's about 50 police officers with their supervisory structure that keeps the bridge open 24/7.
10 years ago, if a car broke down on the George Washington Bridge, the Port Authority would have to wait for the stranded motorist to contact them. Today, the bridge is wired, and the new technology allows the Port Authority to keep tabs on all aspects of the operation.
One of the great tools that we have here at the George Washington Bridge is the Intelligent Transportation System. It's a computer operating system. One of the things that it does for us, it gives us information regarding our roadway conditions. We have roadway sensors strategically located throughout our roadway. They're embedded underneath the asphalt for protection. They give us 2 things. One is basically weather, especially in the wintertime, when it comes to freezing roadways. The other thing it does for us is it gives us an indication of traffic flow and if there's any kind of stoppage to that flow, for instance, an accident or a disabled vehicle.
Once a problem has been detected, bridge personnel can immediately get a good look at the situation. Over 80 cameras are strategically placed throughout the structure.
Some of them are along our walls, some of them might be on light poles, or others might be right in the towers. It helps us expedite the proper personnel to any type of incidents, which makes everything more efficient.
All of the sensor and camera information is relayed to the bridge's control center and allows bridge personnel to manage the traffic flow via lighted signs and radio broadcasts. Even toll collection on the bridge has undergone an electronic makeover. For years, drivers lined up at the toll booths to pay their $6 crossing fee. Today, thanks to an electronic tag known as an Easy Pass, The cars are scanned and charged automatically. But the Easy Pass tags do more than speed motorists through the toll booths. Since traffic moves in both directions on each level of the bridge, motorists have to make a choice. The real-time information collected by the Easy Pass helps drivers pick the level that is moving the quickest.
The Easy Pass tags are part of our intelligent transportation system. By using them as probes in the system with a computer algorithm, we could know how long it takes to travel between two different points by the number of tags that traverse that point. So we can tell our customers if you take the route X or you take route Y, it'll be a certain amount of minutes and might be faster or slower. And in turn, when the customer sees that come up on variable message signs as they approach our roadways, they believe us because they know it's done in real time, and it's like we're reaching into the car and grabbing the steering wheel. The customers will go the shortest route.
But for the Port Authority, there are larger concerns than just keeping the traffic moving. As with all major civil engineering facilities since 9/11, security has become a top priority on the GW. Additional personnel have been hired to stand guard 24/7 at sensitive locations, like the tower foundations and anchorages. Cameras, once used only to monitor traffic flow, also keep an electronic eye out for any suspicious activity.
We've also gotten a security system, which is part of the technology advances that we've made. There's 900 points on the facility that are monitored 24 hours a day, 7 days a week, to ensure that doors are not opened when they're not supposed to, that people aren't accessing areas that are critical to the operation of the facility.
But the bridge's enemies aren't necessarily human. Regular maintenance and long-term renovations are part of the plan to combat the forces of nature.
To give you an idea of what we do in terms of maintenance, we have ongoing right now probably 20 projects in construction. We're spending anywhere from $30 to $50 million over the last 3 to 4 years in terms of construction out at the bridge. In terms of what we're designing and in terms of planning, we have close to 30 projects that we have under design right now.
One of the biggest projects on the docket? In 2006, the Port Authority will begin to build ramps on the New Jersey side, connecting the Palisades Interstate Parkway with the lower level of the bridge. The construction costs for the massive undertaking are estimated at $60 million. The ramp should be open to traffic by 2010.
And any engineer that works on this, you have a sense of pride. We have a sense of ownership of all of our facilities, but particularly the George Washington Bridge, because you go anywhere around the country, anywhere around the world, it's a recognized landmark, and it really gives you a sense of pride to be able to work on a structure like that.
For those entering New York City for the first time, there are other monuments that may be more identifiable. But in a city of great bridges, the George Washington has distinguished itself with those who depend on it most, New Yorkers.
For New Yorkers, the George Washington Bridge is a foremost icon because when they see those soaring steel towers, they know that they're almost home.